TOF 102 webinar on primary and secondary ion optics. In case you haven't seen it, you can view our TOF-SIMS 101 webinar on our YouTube channel. On our YouTube channel, you can also view XPS and AES webinars, as well as software tutorials and more. So feel free to check it out. Today, I will begin with a brief introduction of physical electronics. I will then do a brief overview of the TOF 101 webinar as a review. I will then begin the topic of today and take you on a journey through the nano-TOF spectrometer, beginning with the primary ion path and how the Phi LMIG works. I'll then take you on the path through the secondary ion optics through the TRIFT spectrometer. And I will also go over some examples throughout the presentation to show how these optical elements can affect the TOF-SIMS data. Physical Electronics is a worldwide company with headquarters in Japan, Minnesota, and Germany. Phi is the only full-line supplier of high-performance instrumentation for surface analysis. We supply AES, XPS, HAXPS, DSIMS, and TOF-SIMS instrumentation all under one roof. So as an overview for the TOF 101 webinar, we learned that primary ions are generated in a liquid metal ion gun, or an LMIG. These primary ions are bombarded onto a sample surface and will eject secondary ions from the surface. These secondary ions can be extracted into the spectrometer and will be separated by their time of flight. We will then detect these secondary ions and can use those to generate chemical maps of the sample surface. In TOF 101, we also learned about the static limit. TOF-SIMS is inherently a damaging analysis method. Every time a primary ion particle impacts the sample surface, material will be removed from that surface for analysis. In order to avoid oversampling a surface, we need to stay below what is called the static limit. The static limit is an ion current of about 10 to the 12, 10 to the 13 atoms per square centimeter. Compared to a typical atomic surface density of 10 to the 15 atoms per square centimeter, this means that if we are below the static limit, we will be sampling less than 1% of the sample surface. To show how that works with an image, this is an STM image of a pristine silicon surface. And over here is an image of the silicon surface after it has been exposed to a primary current of 3 times 10 to the 12 ions per square centimeter. Here you can see some spots have been damaged by those primary ions. But as long as we stay below the static limit, we can be assured that statistically speaking, we will always be sampling a pristine area of the sample surface. We also learned that TOF-SIMS is a powerful imaging tool. Here's an example of a human hair and how we can use TOF-SIMS to image the location of sodium lauryl sulfate concentrated on the hair. We also can use TOF-SIMS to analyze pharmaceutical ions. And in this case, we have a cross-section of a rat liver, and we can see where the pharmaceutical drug has been located in the liver. TOF-SIMS is also used in the mineral industry. And in this case, we have some minerals, and we can isolate individual elements in those minerals to determine which domains those elements are in. Finally, in TOF 101, we learned how we can use tandem MS to identify large molecular ions. In this case, we have 2 large organic molecules with the same unit mass. And using tandem MS, we can fragment these large molecules and identify their fragmentation pattern to isolate them. We can then use these 2 different tandem MS spectra to show on the sample image where those 2 different chemicals are located. So now we'll begin the topic of today's webinar, ion optics. Ion optics are similar to visual optics in that they can reflect, bend, focus, and stop ion beams. How they're different than visual optics is that they will use charged electrodes and electric fields to manipulate the ion beams. The fundamental principle of ion optics is that like charges will repel and opposite charges attract. So if a positively charged ion approaches a positively charged plate, it will be repelled away from the plate. If a positively charged ion moves towards a negatively charged electrode, it will be attracted towards that electrode and move around it. We can also use electrostatic fields to create lensing effects. This is an example of an Einzel lens, which has a different voltage potential on two adjacent plates. This creates an electrostatic field between those two plates, and that field will interact with the ion beam. In this case, the first electric field will widen the beam, and the second electric field will then refocus the beam into a focal point. We can also do deflection blanking to stop an ion beam. In this case, we will use the two electrodes to bend the ions away from its flight path, and in this case, it will impact the sidewall of an aperture. If this aperture is grounded, those ions will lose their charge and will not be detected by the spectrometer. I will also talk today a lot about mass resolution. Mass resolution is the ability to separate ions in the same unit mass. So in here, we have a mass spectrum at mass 27. And with enough mass resolution, we can separate the aluminum peak from the C2H3 peak. Mass resolution is calculated as m over delta m. M is the mass at the peak centroid, and delta m is the width of the peak at 50% of the peak height, or full width half max. In general, for TOF-SIMS, m over delta m of more than 10,000 is considered good. For TOF spectrometers, the resolution is determined by the difference in time between the first ions hitting the detector and the last ions hitting the detector within the M to Z window. So the ions that first hit the detector define the leading edge of the peak, and ions at the end of the ion packet will define the tailing edge of the peak. To move on to the hardware, PHI offers 3 LMIG primary ion beams: gallium, gold, and bismuth. And these all have their advantages and disadvantages. And we can also use large cluster primary beams, such as C60 or large argon clusters. In this talk, we will focus on the bismuth LMIG, which can generate 9 cluster ion species listed here. So the first challenge will be to select one of these ions for primary analysis. To begin at the top of the LMIG column, we will store bismuth metal and heat it up into a liquid and ionize it. This will create an electrospray of metal ion clusters. At this point, we are generating all of these ion clusters continuously. We will then focus that ion beam into the quad blanker. The quad blanker will create an ion pulse by repeatedly stopping this ion beam. The quad blanker begins what is called the electrodynamic double blanking LMIG TOF scheme, and this is how we will select one particular primary ion species. At the beginning of the LMIG pulse, we will have all of the ion species existing at the same point in time. As they propagate down the column, they will begin to separate by their mass to charge value. The smaller ions will travel faster, and the larger ions will travel slower. At this point, the ions enter an optical device called the buncher. The buncher will compress the ions into a smaller time-resolved pulse, thus increasing the mass resolution, and I'll discuss this a little bit more momentarily. The ions will then travel into the dynamic blanker, which can be used to select one of the individual primary ion species by preventing the other ones from propagating down the column. So at this point, we are able to create the mass pure ion beam. This mass pure ion beam is then steered into the octopole region. And the octopole region is where we control the raster optics. Rastering is how you can scan a microprobe beam across a sample to analyze a larger area. Finally, the mass pure ion beam is focused through a lens onto the sample surface. So to describe that buncher a little bit more, as the ions exit through the aperture, they enter this buncher device. This buncher is a dynamic electric field that will compress the ion pulse. It does this by slowing down the leading edge of the ion pulse, speeding up the tailing edge of the ion pulse to create a tighter ion packet. This is now compressed to a length of less than 1 nanosecond as it impacts the sample surface, meaning all of the ions in this ion packet will hit the sample in less than 1 nanosecond. This buncher, along with the focusing elements of the LMIG, allows us to operate in what we call the HR squared mode. In HR squared mode, we're able to achieve both high lateral resolution of less than 500 nanometers and high mass resolution at greater than 10,000 m/delta N. Here's an example of how we can use the HR squared analysis mode. We have a sample of some droplets here, and our field of view is 25 microns. So at a mass resolution of 10,000, we are able to resolve these two different organic elements, both at a unit mass of 57. With our high spatial resolution, we can image the 300 nanometer droplet size. And what's more, with our HR squared mode, we can operate under high primary ion current, which means we can conduct this analysis very quickly. And this one took about 6 minutes. All right, so back on our ion optic journey, we're at the point where the primary ions are impacting the sample surface. As the primary ion hits the sample surface, the energy is transferred into the surface and particles are released from the sample. These released particles can be single atoms, elemental clusters, molecular fragments, or intact molecules. And we're interested in, of course, the charged elements because we can extract those into the spectrometer. To extract the secondary ions from the sample, we will apply a voltage to the sample surface. This will repel the ions away from the surface into the extraction lens. This is called an extraction field. There are a few problems with extracting ions from the samples, and that is particularly a problem with rough or non-flat surfaces. So in this particular example, we have an insulating sample that does not conduct the sample potential through itself. And so the secondary ions emitted at the top of the sample will experience a different acceleration potential than ions that are emitted from the bottom of the surface. This is a problem for time-of-flight spectrometers, particularly traditional reflectron spectrometers, because this will create a large kinetic energy spread in the secondary ions. The ions that are emitted with the larger kinetic energy will be faster and impact the detector sooner than ions with less kinetic energy. This will decrease your massive resolution by widening that secondary ion pulse. There's another challenge with extracting secondary ions, and that is that they can be emitted at different angles from the sample. This is particularly true for conducting samples, because as that sample conducts the sample potential through itself, it will create curves in that extraction field. Ions being emitted through that curved field will experience a wider takeoff angle. And again, this is a problem with traditional time-of-flight spectrometers because ions being emitted at an angle from the sample surface will experience a longer flight path and thus take longer to impact the detector, decreasing your mass resolution. The PHI TRIFT analyzer can accommodate both of these problems. TRIFT stands for Triple Focusing Time of Flight, and it is comprised of 3 ESAs, or electrostatic analyzers. And we will use these ESAs to focus the secondary ion beam to the detector. An ESA works by applying a positive charge to the outer plate and a negative charge to the inner plate, and this will bend that secondary ion beam through the ESA. This can accommodate for a wide kinetic energy spread because ions that have a greater kinetic energy will travel deeper into the first electrostatic field, allowing for the ions with less kinetic energy to catch up and impact the detector at the same time. This can also accommodate for wide angles of secondary ions because those ions emitted at an angle will be refocused into the standard ion path through the third ESA to impact the detector at the same time as the on-axis ions. So in this way, the PHI TRIFT analyzer can compensate for both a wide kinetic energy spread and a wide angular flight path. I'll show some examples of how this works with real samples. This is a sample of some organic spheres on a substrate. And since these are insulating samples, the ions emitted from the top of the spheres will exhibit less acceleration potential than the ions emitted from the bottom of the sample. However, because we have a wide bandpass acceptance of the secondary ions, we will achieve high mass resolution at the top of the sample and at the bottom of the sample, and thus we can identify both of these organic ions. Another example of how we can optically image a deep sample is this VIA sample here. So this is about a 70 micron deep sample, and in one analysis, we can analyze the top of the surface, the inner wall, and the bottom of the well. And we can tilt this sample to image the different components of it simultaneously. And here's an example of how we can accept a wide angle of the secondary ions. So this sample is a copper electrode plated with gold on a polymer resin. So if we can angle the primary ion beam at this vertical edge of the copper electrode, we will be able to image the gold surface, the vertical copper edge, and the polymer resin all in one analysis. And this is all because of the TRIFT's wide angle of acceptance for these secondary ions. There are some limits, and if you need to analyze a sample that goes beyond the capabilities of the TRIFT, we have another tool, and that is called FIB-TOF imaging. FIB stands for focused ion beam, and we can use that to carve out a portion of the sample. So here we have a metallized polymer, and we can cut into this sample and then in one angle and image it from the other angle to see that cross-section of the sample. So this is a sneak peek of our FIB-TOF technology, which will be the topic of a future webinar. The TRIFT spectrometer has another benefit, and that is that it can accommodate for metastable ions. Metastable ions can undergo what is called post-source decay, in which they fragment while they're flying through the flight path of the spectrometer. These fragment ions will have a much larger velocity distribution and will significantly reduce the mass resolution. However, because these product ions will have less energy than their precursor ions, they will travel in a much shorter path through the first ESA, collide with the inner electrode, and be eliminated. So in this way, the TRIFT spectrometer automatically filters out the metastable ions. I will now discuss some additional optical elements of the TRIFT spectrometer, and those are the high mass blinker, contrast diaphragm, energy slit, tandem MS picker, and the dual microchannel plate detector. First in the flight path is the high mass blinker. The high mass blinker is an essential component in a time of flight spectrometer, and this is because high mass ions may be extracted from the sample. If a high mass ion has a time of flight that's greater than the duty cycle of the spectrometer, this will cause a wraparound effect. I'll show how that works here. So the duty cycle of the spectrometer is the mass window that you're analyzing. In this case, we'll say we're analyzing between 0 and 2000 m/z. If an ion has a mass of 1000, it will take about half of the duty cycle to fly through the spectrometer and hit the detector, and that will be recorded as a mass of 1000. However, if an ion has a mass of 3000 from that first duty cycle, it will take longer than the duty cycle to fly through the spectrometer, impact the detector during the second duty cycle, and in this case, it will be recorded as a mass of 1000 rather than 3000. This can be true for even larger ions that may take 3 duty cycles or more to travel through the spectrometer. So what the high mass blinker does is it will stop that ion beam at the point where the last ions from the window will have passed this early flight path point, thus preventing those large mass ions from entering the spectrometer. The next optical element in the flight path is the contrast diaphragm. The contrast diaphragm is a selectable size aperture that can be used to remove the edges of that ion beam. This will limit the angular spread of the ion beam, resulting in tighter ion packets and higher mass resolution. An example of how that can work is shown here. This is a spectrum at a unit mass of 27. And with the CD out or open, we will accept all of the ions from that sample and have a relatively wide peak and low mass resolution. With the CD in, limiting that angular spread of the ion beam, we can eliminate the tails of this peak, getting a much higher resolution peak. And we now see we have enough resolution to isolate the aluminum peak from the C2H3 peak. The next component in the flight path is the energy slit. By utilizing the dispersive nature of the first ESA, an energy slit can be used as a filter to isolate either organic or inorganic ions. And we can do this because the inorganic ions tend to have a much larger energy spread than organic ions. And what that means is that as they enter the first ESA electrostatic field, the inorganic ions will take a wider flight path than the organic ions. And if there are metastable ions, as I mentioned earlier, they will have a shorter flight path through the first ESA. So the slit can be moved to isolate any of these flight paths. To show how that works, I have a spectrum here that shows nickel with some interferences between some organic ions. With the kinetic energy filter in place, we can isolate only that nickel ion and remove those organic ions from the spectrum. This also has an impact on the image quality. So with no kinetic energy filter, we'll have that noise from the organic ions here. But with that filter in place, we can remove that noise and increase the contrast of those nickel ions in the image. This kinetic energy filtering is an inherent and unique capability of PHI's TRIFT spectrometer. The next component in the flight path is the tandem MS precursor selector and CID cell. And I will stepwise go through how this precursor can select ions for collision in tandem MS. So first, the ions will enter the picker. And now the ions are fully time resolved, so we can select a single mass to charge window in the center of this picker. We can then deflect that single mass to charge window ion into the collision cell and allow the rest of the ions to continue traveling to the MS1 detector. And this way, we are able to conduct a lossless tandem MS experiment because none of the signal from the unselected ions is lost in this process. The ions selected for fragmentation will enter the fragmentation chamber, impact with argon atoms, and be fragmented into product ions. These product ions will then continue on through another time of flight tube in the MS2 detector to generate a tandem MS spectrum. This was another sneak peek of our tandem MS technology, which will also be the topic of a future webinar. The final element in our ion optical journey is the MCP detector, or microchannel plate detector. As the ions impact the MCP detector, they will generate some secondary electrons, shown here. These secondary electrons will also impact the walls of this microchannel plate and begin a secondary electron cascade through the microchannel plate. This will drastically amplify the signal of electrons that were generated from one single primary ion or secondary ion. These electrons, as they impact the phosphor screen, will impart a voltage on that phosphor screen. When this voltage reaches a certain potential, it will generate a count in the computer. We also can calculate the mass of this secondary ion based on the time it takes from the primary ion pulse to travel through the spectrometer to impact the detector. So we now have the abundance or the count based on how many ions hit the microchannel plate and the mass of that ion, so we can generate our mass spectrum. And thus our journey through the spectrometer is completed. So in summary, We went on a journey through the Phi LMIG column, in which we learned how the electrodynamic double blinking LMIG TOF scheme allows us to generate a mass pure ion beam. We also learned how ion beam bunching and focusing can allow us to undergo HR squared analysis mode, which allows us to analyze samples using both high mass and spatial resolution. We then traveled through the TRIFT spectrometer, a triple ESA spectrometer that can accept large kinetic energy bandpass and a wide angle of acceptance of secondary ions. We learned how the angular diaphragm and energy slit can be used to fine-tune the spectrometer performance, and we had a sneak peek into tandem MS and FIB-TOF technology.